In this final segment of the block, I want to talk about abstraction in general, but in particular as well about how we turn recursions into functions, the so-called folding functions. Let's get started by setting the scene though. Abstraction in general is spotting patterns in data or computation and representing that pattern directly in the language. So we've seen abstraction through polymorphism. We can use the same code at different types. So for example, the twice function, which takes a function from a type to itself and applies the function twice. We can use that at whatever function type we like, as long as the function has the same input and output types. We can similarly apply map at any type, transforming lists of elements of one type to lists of elements of another. So that's abstract in terms of its type, but also in terms of the transformation it makes, which is passed in as a function. So we're getting abstraction through polymorphism, but also through higher order functions. What I want to talk about in this section is abstracting away from recursion. And here you see, this is a typical example of the sort of recursion we do over lists. It's called insertion sort. It works by inserting the element at the head of the list into a sorted version of the tail. And the insertion puts the element in the right place, assuming that the list is itself sorted. So those both insert and sort here are defined using primitive recursion over lists. Now, in general, the pattern for recursion over lists is something like this. It says to define foo, give a value for the empty list, and then give a value for the non-empty list, x cons x's, using the value x and foo of x's. So in terms of the sort function, what we do is we've got the value at the empty list, is here the empty list, and the way we use x and sort x's is that we apply the function insert to them. So in general, what we do is to make a recursive definition. At the empty list, we have some value s, and for the non-empty list, we say that f on x cons x's is the function g applied to x and f of x's. So what we have there is that general pattern that defines f. Now the next step we can take is say, well, we can actually turn this into itself into a function. And what we do is it's what's called the foldr function. And foldr takes these two arguments, g and s, and an empty list, and it returns s. When we give foldr g and s x colon x's, it returns g applied to x and the result of foldr on g, s and x's. So you can see that what foldr g of s is precisely the f I defined up there using s and g. But foldr does this for any g and any s. So foldr is the function that embodies primitive recursion over lists. Now, here's the function. Again, and it has this type. It takes a function g, which takes an element A, element of type A, element of type B, and returns something of type B. It takes a starting value of type B, and it gives us back a function from list of A to B. So if we apply foldr to G and S, we get a function from list of A to B. So this is precisely, if we do that partial application, we're getting that recursive function defined on list of A and returning a B. An example is that sort is foldr of insert and the empty list, and you can define map in this rather convoluted way. It does a foldr on the function that takes an A and applies f to it, and then conses that on the front of its argument. Now, why is this called fold right? Let's do an experiment. Let's sort of unfold, as it were, this application of foldr. What happens first of all is we take x1 off the list, apply g to that and foldr on the remainder. And again, we apply then g to x2 and foldr on whatever is left. And repeating that, we get down to the final case where we have an empty list and foldr gs on that empty list gives us just s. And so we've got this repeated application of g through the list. But if we turn g into infix, you can see even more clearly what we've done really is fold the function g into the list with the starting value s. So instead of having the list x1, x2, x3 down to xn, what we've got now is x1, g, x2, g, and so on. We've folded the application of that function g into along the list, and we've folded it from the right. So we start applying g at the end of the list and then recursively build outwards. So that's why it's called fold right. Now, could we do a fold left? What would a fold left look like? Well, let's see what it might look like. We start off with a list. We want to fold this function g. We start off with the list x1 to xn, and we have a starting value s. What do? Well, we want to somehow combine that value s with x1 using g. But then we want to fold into the rest of the list. So that looks a bit like this. We would combine s using g with x1, and then we'd call foldl again. And we do that repeatedly. And we would get down to the empty list, and indeed then we would have something where what we had done was fold g into the list from the left, with this starting value on the left as well. So there you see this pattern of fold left, and as a definition, here's the definition of fold left. On an empty list we get the value s. On the non-empty list we apply g to the value of s and x and make that the new starting value and apply foldl to the rest of the list. So you can see that this is a tail recursion. So maybe it's a more efficient implementation. The folklore is that tail recursion is better. It's more like an imperative loop. We know that it is like an imperative loop, but is it really more efficient? Well, we'll come back to that in a couple of blocks' time when we talk about lazy evaluation, which is how evaluation works in Haskell. But certainly, whatever the case, foldl is the function that represents tail recursion in the same way that foldr represents primitive recursion.